We previously saw how linear transformations on general vector spaces can be represented as matrices, link in the description to that lesson. This used a sort of roundabout method involving coordinate vectors, and necessarily, since it involved coordinate vectors, it was dependent on the bases that we chose to use for the domain and the codomain of the linear transformation. So if we consider a linear operator, which takes us from a vector space V to that same vector space in some way, there are many matrices that could represent this operator depending on the basis that's chosen for V. And we may consider what relationship exists between them, or which basis could lead to the simplest transformation matrix. We'll begin with a quick example showing a transformation matrix with respect to a particular basis, and then a more simple transformation matrix that results from using a different basis. Throughout the rest of the video, we'll investigate the connection between matrices for the same linear operator with respect to different bases, and in the end be able to make a lot of new definitions with regard to linear operators that we previously only made with respect to matrices. So for example, consider a matrix operator from r squared to r squared, whose matrix relative to the standard basis for r squared is seen here. So the transformation matrix for t relative to the standard basis S is this 2 by 2 matrix. Now let's see a simpler matrix for this same transformation, but with respect to different bases. As nice as the standard basis is, it's not always going to result in the simplest transformation matrix. Indeed, this operator actually has a nicer matrix relative to the basis B consisting of these two vectors. Let's construct the matrix relative to this basis and see just how nice it is. You should recall from previous discussions that to construct the matrix relative to this new basis, we need to find the images of these new basis vectors under the transformation. So to do that, we take u1 and multiply it by the transformation matrix for t relative to the standard basis. That gets us to this vector 3, 3. Similarly, the image of the other basis vector, u2, is found by multiplying by the transformation matrix, and we get this vector for 8. Now, we need to express these images with respect to the new desired basis, and we see that the image of u1, 3, 3, is just 3 times u1. Similarly, the image of u2, 4, 8, is actually just 4 times u2. Thus, the coordinate vector of the image of u1 with respect to the new desired basis is 3, 0. We need 3 of u1 and none of u2. And the coordinate vector of the image of u2 with respect to the new basis we see is 0, 4, because it has 4 of u2 and 0 of u1. These coordinate vectors relative to the new basis can be used as the columns of the transformation matrix relative to the new basis. And we see that here. To construct the matrix for the linear operator t relative to this basis b, we construct the matrix whose columns are the coordinate vectors of the images of the basis vectors of the new basis with respect to the new basis. And we see that is this matrix with 3, 0, in the first column. That's the coordinate vector of the image of that first basis vector relative to the new basis. And we have 0, 4 in the second column. That's the coordinate vector of the image of the second basis vector with respect to the new basis. Of course, this is a very nice diagonal matrix. The original matrix that we had with respect to the standard basis was not diagonal. Since this transformation happens to have the effect of tripling u1 and quadrupling u2, they make better basis vectors for this transformation, at least as far as the transformation matrix and its simplicity is concerned. So you can see why we may at times want to consider the transformation matrix for a linear operator with respect to one basis over another. It may yield a simpler matrix. In this course, we will not be able to study this problem of finding the simplest transformation matrix in any depth, but in the rest of this video, we will see a deep connection between the transformation matrices for a linear operator with respect to different bases. bases. In order to understand this connection, an important theorem is necessary, and to understand the theorem, let's make sure that we're all brushed up on transition matrices. I'll leave a link in the description to my lesson where we originally covered transition matrices, but let's just do a quick recap. If B and B prime are these two bases for the vector space V, then this is how the transition matrices between those bases are constructed. The transition matrix from the basis B to the basis B prime is the matrix whose columns consist of the coordinate vectors of the old basis relative to the new basis. So notice that. To go from old basis to new basis, we take the coordinate vector of u1, the first old basis vector, with respect to the new basis b prime. And then the second column is the coordinate vector of the second old basis vector, u2, with respect to the new basis b prime, and so on. The nth column of the transition matrix is the coordinate vector of the nth old basis vector with respect to the new basis b prime. This is how we get from b to b prime. If we take a vector from v, its coordinate vector with respect to that old basis b, you can take that and multiply it by the transition matrix from b to b prime, and then get its coordinate vector with respect to that new basis b prime. And we can go the opposite direction in a similar way. If we want to transition from the new basis to the old basis, we use this transition matrix. Its first column, for example, is the coordinate vector of the first new basis vector with respect to the old basis, and so on. This is the transition matrix from b prime to b. If we take any vector v from this vector space, its coordinate vector with respect to the basis b prime can be multiplied by this transition matrix from b prime to b to get the coordinate vector with respect to b. And of course, since one of these transition matrices takes us from b to b prime, and the other takes us from b prime to b, it should be no surprise that these will be inverse matrices. But then here's the interesting thing that ties this back to linear operators. Since transition matrices change the basis used to express vectors, but without actually changing the vectors themselves, we can regard transition matrices as being the transformation matrices for identity operators. A transition matrix on a vector space V from a basis B to B prime is just like an identity operator, since it's not actually changing the vectors, it's just changing the bases. Hopefully that feels intuitively correct, but let's go ahead and prove it. If B and B prime are bases for a finite dimensional vector space V, and if I from V to V is the identity operator on V, then in fact the transition matrix from B to B prime is the transformation matrix for the identity operator relative to the bases B and B prime. Similarly, the transformation matrix from B prime to B is the identity operator's matrix with respect to B prime and B. The proof follows very easily if you recall how transformation matrices are constructed. For the proof, we would let B be this basis for V, and B prime be this basis for V. Then, the matrix for the identity operator with respect to the bases B and B prime is constructed like this. We've previously gone over how, in general, this is the method used to construct a transformation matrix from a basis B to a basis B prime. Its columns consist of the coordinate vectors of the images of the old basis vectors relative to the new basis. So this first column, for example, is the coordinate vector of the image of u1, the first basis vector, with respect to the new basis. This second column is the coordinate vector of the image of the second old basis vector with respect to the new basis, and so on. Note that right now we're just proving this part, that the transformation matrix from B to B prime is the matrix for the identity operator with respect to the bases B and B prime. The other direction would be just the same proof, just with things swapped around. So we're just going to worry about that direction. Now, coming back to this transformation matrix, well, remember, I is just the identity operator. So I know what I of u1 is, I know what I of u2 is, and so on. I of u1 is just u1. It's the identity operator. It doesn't change anything. I of u2 is just u2. I of un is un, and so on. Hence, the matrix for the identity operator with respect to the bases b and b prime is in fact just this matrix, whose columns are the coordinate vectors of the old basis vectors, but with respect to the new basis. And that is exactly how a transition matrix is constructed. Clearly, this is the transition matrix from the basis B to the basis B prime. And in a similar way, we could show that the matrix for the identity operator is the transition matrix from B prime to B as well. Now, having this understanding of identity operators as transition matrices between bases, we're prepared to answer this question of the relationship that exists between matrices for the same transformation relative to different bases. So we're going to let B and B prime be bases for a finite dimensional vector space V, and of course T is a linear operator on this vector space. Then we're going to consider the following composition of transformations. We start off with a vector V in our vector space V with respect to the basis, let's say, B prime. Then we use the identity operator on V, which of course just takes us to V, but let's suppose it also changes the basis from B prime to B. So the basis has changed, but of course not the vector, because we've used the identity operator. Then let's say we apply this transformation T, this linear operator. That of course takes us from V to whatever its image under the operator is, T of V, but we're still in the vector space V, and we have not changed the basis. So it was B, and it still is B. But then we apply another identity operator, which of course is not going to change T of V, it's still just T of V, and we're also still in the vector space V. But let's say this identity operator changes us back to the basis we started with, B prime. So what are we looking at here? Well, if we don't pay any attention to the bases, we're just looking at the linear operator T. We started with V, and we ended at the image T of V. And overall, the basis didn't change. It started as B prime, it ended as B prime. So in that way, we're just looking at the linear operator T written as a composition of three transformations. The identity composed with T composed with the identity. But if we do pay attention to the bases and then express these operators as their transformation matrices, we see that we have this equation. Overall, we have the matrix for the linear operator T with respect to B prime, because we started at V with respect to B prime, and we ended at T of V with respect to B prime. So on the left side of this equation, writing everything as matrices, we would have the matrix for the linear operator T with respect to B prime. On the right side, we first have the matrix for the identity operator with respect to the bases B prime and B, which we see there. And then in the middle, we would just have the matrix for the linear operator T, but with respect to the basis B, because T is taking us from V to T of V, but with respect to that basis B. So that's what we see there. And then finally, we have again an identity operator, but taking us from the basis B to the basis B prime, and that's what we see there. Note that in this transformation matrix notation, the final basis is written first. So for example, this last identity operator takes us from B to B prime, and so in its matrix notation, we see that the B prime is written first. So once again, this equation just comes from writing this equation consisting of a composition of operators, but instead we're just writing it as their transformation matrices. The effect of composing linear operators is the same as multiplying their transformation matrices. But then what we see is the transformation matrix for the linear operator T with respect to one basis equals this identity operator times the transformation matrix for the linear operator T with respect to this other basis times this other identity operator. And so if we view those identity operators as transition matrices, we could rewrite the equation like this. We have the transformation matrices for the linear operator T, but with respect to different bases, and one equals the other, except getting multiplied on the left and right by some transition matrices. On the left is the transition matrix from B to B prime. That's coming from this identity operator. And on the right is the transition matrix from B prime to B, which is coming from this identity operator. But we know these transition matrices are inverses. Hence, if we just call the one on the right P, what we have is the matrix for the operator with respect to B prime is actually equal to P prime times the matrix for the operator with respect to the other basis, B, times P. In other words, what we have here is similarity. This transformation matrix is equal to P prime times this times P, so by definition, it's similar to this transformation matrix. And so we've established half of this theorem. I'll leave a link in the description if you want to check out the proof of the other half, but we're going to take the other half for granted in this video. If V is a finite dimensional vector space, then two matrices M1 and M2 represent the same linear operator on V if and only if they are similar matrices. Furthermore, if M2 is equal to P inverse M1P, then P will have to be the transition matrix from the basis used for M2 to the basis used for M1. That's just like what we saw in our justification. This P on the right is the transition matrix for the basis used for this guy to the basis used for this guy. So transformation matrices for the same linear operator, not only do they have to be similar, but specifically the matrix P that would demonstrate their similarity is a transition matrix that goes from one basis to the other. For an example, consider those transformation matrices that we discussed before. Let's call this one C, and we'll call the diagonal one D. We know they represent the same linear operator from r squared to r squared with respect to the appropriate bases. And so, by the preceding theorem, these matrices C and D must be similar, and we may seek a matrix P that demonstrates this, so that P inverse CP is equal to D. Also, from the preceding theorem, we know that the matrix P that will demonstrate this similarity is the transition matrix that takes us from what was really our new basis, B, to the standard basis, S. And we know how to construct a transition matrix like this. It's the matrix whose first column is the coordinate vector of our first basis vector with respect to the target basis, and whose second column is the coordinate vector of the second basis vector with respect to the target basis. And this is that basis B that we were using in the original example. Of course, this is very straightforward. The coordinate vector for our first basis vector with respect to the standard basis is just 1, 1. Similarly, the coordinate vector for the second basis vector with respect to the standard basis is just 1, 2. And so the transition matrix we're looking for, the matrix P, which we can use to demonstrate similarity, is this one, with 1, 1 as its first column and 1, 2 as its second column. And of course, this is a 2 by 2 matrix. It's straightforward to find its inverse, which is this matrix here. Remember, that requires us to divide by the determinant, which is 1, and then just swap these two entries, and then negate those two entries. And that's how we arrive at this inverse matrix. And then you can verify that indeed this matrix D, which was a matrix for the linear operator with respect to the basis B, this is equal to the original transformation matrix with respect to the standard basis, but multiplied on the left by P inverse, and multiplied on the right by P. So again, we're seeing this theorem in action, that transformation matrices for the same linear operator are in fact similar, and the matrix that will demonstrate that similarity is a transition matrix between the bases. And now we can make a pretty big generalization in terminology. Previously, you might have said that the determinant of a linear operator doesn't make any sense, because determinants are defined on matrices. Then you might have said the determinant of a linear operator could make sense, because we can represent linear operators as matrices, but it still really wouldn't work because we can represent a linear operator as different matrices depending on the bases that are chosen. But now we can say that indeed the determinant of a linear operator does make sense, because even though we can represent a linear operator with different matrices depending on the chosen basis, those matrices have to be similar. And so the properties which are invariant between similar matrices will also be invariant between matrices for linear operators with respect to different bases. We've just established an equivalence between similar matrices and matrices for the same linear operator. So everything we've previously discussed as similarity invariants of matrices can also be regarded as similarity invariants of linear operators. And here's a brief table of some of the most important similarity invariants. If T is a linear operator on V, and B is any basis for V, then the determinant of the transformation matrix for T relative to the basis B is the same as the determinant of any matrix that's similar to that, which would be a matrix for the same operator, but with respect to a different basis. Similarly, the matrix for T relative to B is invertible, if and only if any similar matrix is invertible, and so on. Of course, the matrices we began this video with make another good example here. The determinant of those two transformation matrices should be equal, because they're matrices for the same transformation, just with respect to different bases. This matrix was with respect to the standard basis, and this matrix was with respect to that other basis B. They gotta have the same determinant because they're matrices for the same linear operator. And indeed, we see they do. The determinant of the transformation matrix relative to the standard basis is 10 minus negative 2, so 12. And the determinant of the transformation matrix with respect to that new basis B is 12 minus 0, so 12. Again, this means that the determinant of a linear operator is something that makes sense, because however you choose to express that operator, whatever basis you use, the resulting matrix will have the same determinant, no matter which basis is chosen. This even means that something as seemingly wacky as eigenvalues of a linear operator is indeed something that makes sense and is defined. To find the eigenvalues of the linear operator on P2, defined like this, for example, all we have to do is find the matrix for the transformation with respect to any basis, doesn't matter which one we pick, just gotta find one, and then find the eigenvalues of that matrix. So since this operator takes us from P2 to P2, we'll use the standard basis for that space, which consists of 1, x, and x squared. And the matrix for this linear operator with respect to the standard basis is seen here. In the first column, for example, we have the coefficients of A. This would be in the constant slot. A has a coefficient of 1. And then in the x slot, A has a coefficient of 1. And then in the x squared slot, A has a coefficient of negative 3. In the second column, we do the same thing for B. In the constant slot, B has a coefficient of negative 1. In the x slot, B has a coefficient of positive 3, and so on. So to find the eigenvalues of this linear operator, we need only find the eigenvalues of this matrix for the operator with respect to the basis that we chose. You can verify that these are the eigenvalues of this matrix, and hence the eigenvalues of the linear operator. No matter which basis we chose and the resulting transformation matrix, we would have got the same set of eigenvalues. So that's a bit about the transformation matrices for linear operators with respect to different bases and the relationship that exists between them. Importantly, they are similar, and so of course they share all similarity invariants that we've previously discussed for matrices in general. Let me know in the comments if you have any questions, and be sure to check out my linear algebra course and linear algebra exercises playlists in the description for more. If you find my videos helpful, please consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to additional videos and extra practice, and if you join at the premium tier or above, you can access the lecture notes used in this course. Thanks for watching.